Hi guys, welcome to video lecture 1, Convection in the Atmosphere and the Oceans. Convection is probably a word that you heard a lot when you studied heat transfer in the 6th grade. Along with radiation and conduction, convection is a way that heat energy is transferred through matter. But unlike radiation and conduction, convection only happens in fluids. Fluids are liquids and gases, states of matter where molecules can move around freely. Convection is a small idea that has huge implications for Earth's climate, weather, and oceans, because Earth's atmosphere and oceans are fluids. Go ahead and pause the video and record the essential question in your notes. To really understand convection, we have to revisit another concept you learned about in the 6th grade, density. A convection current is the movement or transfer of heat in fluids, and it depends on the relationship between three properties of matter: temperature, density, and pressure. Check out the picture on this slide. It probably got cold enough over the break that your dad or mom finally turned on the heater. You don't see hot radiators in many homes nowadays, but just think of it as a fireplace or any ordinary heater. The radiant energy from a fire or a heater warms the air around it. When a fluid like air gets warmer, the molecules move faster and spread out. Remember the equation for density from the 6th grade? Density is equal to mass divided by volume. If air spreads out because it's hotter, the space it takes up, its volume, increases. But it still has the same mass. It's still the same air molecules, just spread further apart. In other words, when you heat air or any other fluid, it becomes less dense. Remember dropping things in water to see if they would sink or float? If a block of wood sinks in water, it's more dense than the water. If it floats, it's less dense than the water. Less dense fluids tend to rise, and denser fluids sink. That's why oil floats on top of water. But the temperature of the fluid matters too. Warm air next to the furnace becomes less dense, causing it to spread out and rise up. When the warm air travels across the room away from the heat source, it cools. It becomes more dense and it sinks. You probably get how temperature and density work to make air or water rise and fall in a convection current, but why does the air in this picture move across the room? First away from the heater and then back towards it. That's where pressure comes into play. Pressure is the force of something weighing down on you, or at least that's the definition that we'll use for this unit. Have you ever dived to the bottom of a swimming pool? You can feel the weight of the water pressing down on you. It makes your ears pop and it's kind of uncomfortable. That's pressure. The more matter there is weighing down on top of you, the higher the pressure you feel. That's why submarines can only go to certain depths. If they go too deep, the pressure from the water above them will crush them like a soda can. We're used to it because we experience every moment of our lives, but the atmosphere around us, the air, is made of matter that weighs down on us or exerts pressure on us. So how is pressure related to density in this convection current? If you have warm rising air, it creates an area of low pressure. Warm air molecules are far apart, so there aren't as many of them to exert pressure or weigh down on whatever is below them. Conversely, dense, cold air creates area of high pressure because there are more molecules packed together to exert pressure on whatever is below them. Fluids always move from areas of high pressure over here to areas of low pressure. It's like stepping on a banana. The banana will squish out from under your foot an area of high pressure to any area that is lower pressure. That's what causes the air to move from one end of the room to the other. Okay, in summary, convection currents are caused when fluids are heated. If you increase the temperature of a fluid, its density decreases and it creates an area of low pressure. If you decrease a fluid's temperature, its density increases and creates an area of high pressure. These changes cause the fluid to flow in a circular convection current, distributing heat throughout the entire fluid. So what does convection have to do with earth science? Turns out, a whole lot. Remember, because the Earth is a sphere, it isn't heated by the sun's radiation evenly. The equator receives direct sunlight, but the more you move towards the poles, north or south, the less direct the sunlight gets. This causes the equator to be much warmer and the poles to be much colder. I know, this is old news to you, but this unequal heating leads to convection in the atmosphere and the oceans. It's just like the heater in the picture from the last slide. Thermal energy is distributed from the equator to the poles in the atmosphere and oceans in giant convection currents, from warm to cold, and from the cold poles back to the warm equator. In the atmosphere, you experience this as wind, and in the oceans, as ocean currents. Well, it's not actually that simple. You would think that there would just be one large convection cell in each hemisphere, going from the equator to the poles. But there are actually three, at least in the atmosphere. Air from the equator cools and falls to the Earth long before it reaches the poles. And the polar air gets warm enough to rise long before it makes it to the equator. Because of this, the northern and southern hemispheres have three convection cells. The Hadley cell is closest to the equator, the Ferrel cell is next, and the polar cells are furthest from the equator. Notice that at some points you have air from two cells rising. This creates low air pressure zones and climates like the tropics and the rainforest. And over here you have cold, dense air falling from two cells in the same line of latitude. This creates an area of high air pressure, creating desert climates. You've experienced these convection cells, the movement of air in the atmosphere, as wind. Notice that global winds, represented by these curved red and blue arrows, they don't go straight from the equator to the poles either. Instead, they curve east and west. We'll talk about that in the next video, but for now it's enough to say that it has to do with the rotation or the spinning of the Earth. Convection doesn't just generate wind on a global scale, though. It can happen locally, too. Air takes on the characteristics of the land or the water underneath it. So wind can happen anytime there is air above a warm surface and a cool surface. When you feel the wind blowing on your face, see, here you are right here, what you're feeling is the rush of cooler, denser air going from an area of high pressure to an area of low pressure, where warmer, less dense air is rising. You're feeling part of the movement of a convection current. One great example of this is land and sea breezes. The sun heats land up very quickly during the day, and it cools off very quickly at night. Water, on the other hand, heats up very slowly during the day, but once it's heated, it stores thermal energy very well. It takes forever to cool off at night. If you stand on the beach in the middle of the afternoon, the wind will be blowing toward the land. The sand heats the air rises, and you have an area of low pressure. Over the water, which is cooler, the air is cooler. It's denser. And there's an area of high pressure causing or pushing air toward the beach. The exact opposite happens during the night. At midnight, on the exact same beach, the wind would be blowing out to sea because the land becomes the cool surface in the convection current, and the water, which retains its heat, becomes the warm surface, reversing the convection cell. Convection also happens in the oceans, since water is a fluid and the Earth is heated more at the equator than the poles. There are really two types of ocean currents, though: surface currents and deep ocean currents. Surface currents are caused by wind, which itself is caused by convection, as we just saw. Wind which pushes water in definite patterns. Deep ocean currents, though, are caused by convection in the seawater, along with the amount of salt in the water, which contributes to its density. Unlike the air, though, ocean currents caused by convection are restricted by the continents, which is why this map of deep ocean currents doesn't look like a clean-cut convection cell. Regardless, whether it's wind in the atmosphere or ocean currents, the sun's unequal heating of Earth's surface causes convection in its fluids, moving heat energy around in the air and ocean, creating Earth's climate and its weather.